In the evolving landscape of educational systems, creating optimal high school timetables continues to pose a significant challenge. The increasing demand for personalized and flexible learning experiences necessitates innovative solutions that cater to the diverse needs of students. This paper introduces an extension of the XHSTT format, which supports the encoding of flexible student course choices and class formation requirements in an adaptive manner. The proposed extension addresses the limitations of traditional constraint encoding, enabling the representation of each student's individual academic interests. The need for this innovation became apparent through recent research on timetabling demands for schools across Central Europe, highlighting a trend towards enabling students to follow their individual interests. Although similar to the post-enrollment-based course timetabling (PECTT) problem and the university course timetabling problem featured at ITC 2019, the proposed constraints provide additional flexibility by allowing students to specify preferences and alternatives in their course selections. The new constraints are designed to model student choices on the individual level, making them particularly suited for high school instances rather than university settings. An ILP formulation extending the state-of-the-art ILP formulation by Christensen et al. Is provided, along with 18 publicly available instances that include the new constraints. Initial results for upper bounds using the ILP are also presented. The paper is structured to introduce the new constraints, their usage, and examples of encoding them. It further discusses the potential for future research and improvements in automatic timetabling for modular high schools. The research introduces individuality into high school timetables by extending the XHSTT format to accommodate recent trends of giving students more course choices. This extension includes new constraint categories for student choices, class size requirements, and class size balance. The student choice constraint is designed to model course choices, teaching preferences, and other requirements. It includes parameters such as student IDs, course preferences, and weights for each choice. The constraint also considers the minimum and maximum number of courses a student can attend. The extension aims to provide a unified way to encode timetable requirements, reflecting recent developments and the challenges faced by schools in creating timetables. The new constraints are based on a study involving European experts, ensuring they are practical and useful for real-world scenarios. The research provides a benchmark set for modular high school timetabling and outlines possible directions for future research. Here is a combined summary of pages 5 and 6. The student choice constraint is introduced to model individual student preferences in high school timetables. This constraint applies to each resource, ensuring that each resource attends at least the minimum and at most the maximum number of event groups specified. The deviation of this constraint is calculated as the number of event groups attended that exceed the maximum or fall short of the minimum. This constraint can also be used to encode weighted preferences by adding soft constraints with different weights. Class sizes are another crucial aspect of high school timetables, with limitations due to room capacity, pedagogical restrictions, or legal reasons. In traditional systems, class sizes are determined before scheduling individual lessons. However, with student choices, this approach becomes complex, and a more dynamic approach is needed. The XHSTT format is used to model these restrictions, consisting of times, resources, events, and constraints. Events have a duration and are assigned to time slots, with solution events specifying resource requirements. To model class sizes, 3 resource types are assumed: teachers, rooms, and individual students. For courses with fixed classes, students can be directly assigned. For courses built by the solver, 3 event types are created: a main event for time assignment and resource preferences, events for each student resource required to fulfill the minimum student number, and hard constraints to ensure only chosen students are assigned and all events have a student assigned. Additionally, a hard avoid split assignments constraint is added to prevent different student assignments for sub-events of the same event. This approach allows the solver to dynamically group classes based on student choices and schedule constraints. The research discusses introducing individuality into students' high school timetables by incorporating constraints that ensure each student has a unique schedule. This involves creating minimum requirement events and maximum requirement events to manage student choices and resource allocation. The approach avoids combining student requirements into a single event to prevent exponential enumeration of resource assignments. Instead, it uses student choice constraints to allow students to choose between classes while ensuring a balance in class sizes. To achieve this, balanced class size constraints are introduced, which limit the difference in class sizes to a certain threshold. The constraints are modeled using a novel ILP formulation that extends existing work by incorporating the new constraints. This approach allows for more flexibility in scheduling while ensuring that each student's schedule is unique and class sizes are balanced. The extended modular XHSTT problem introduces individuality into students' high school timetables. It involves several sets of entities, including times, time groups, resources, events, event groups, event resources, subevents, and constraints. The problem also uses various variables such as binary indicators for subevent start times, resource assignments, and deviations from constraints. In addition to these, the model employs functions to calculate the cost of constraint violations, including a sum cost function, a sum square cost function, and a square sum cost function. These functions utilize weights and upper and lower bounds on constraints to determine the deviation values. The model further introduces dummy resources and times to represent no resource or time assignments, respectively. Durations for events and subevents are also defined. The constraints in the model are applied to events, resources, and event groups, with each constraint having a weight and an upper and lower limit. The deviation at a point of application is calculated using the function BCV, which considers both upper and lower bounds on constraints. The objective of the model is to minimize the total cost of constraint violations, taking into account the weight of each constraint and its deviation. This requires solving an optimization problem that balances the need to satisfy all constraints while minimizing the overall cost. The research introduces individuality into students' high school timetables by extending the objective function to include new constraint types. The objective function now considers the costs of hard and soft constraints, deviation from new constraints, and additional terms. Novel constraints link variables to express properties, ensuring balance in class sizes and student choices. The model size was reduced by eliminating variables that would never be used for an acceptable solution, focusing on feasible subevents. The evaluation uses 18 high schools in Germany as a benchmark, considering the diversity in secondary educational systems. This approach aims to create more personalized and efficient timetables, addressing the complexity of student and event constraints. The research introduces individuality into high school timetables by leveraging the UNTI's GmbH dataset, which includes scheduling problems from various schools worldwide. The dataset was anonymized and then translated into the XHSTT format for encoding constraints. This process enabled the creation of more instances in the future. The instances are characterized by complex constraints, including student and teacher availability, subject attendance, and global constraints on lunch breaks. The complexity is further increased by varying school sizes and proportions of modular events. Tables 1 and 2 provide statistics on the instances, including the number of events, students, classes, teachers, and rooms, as well as the number of choice and balance constraints, and modular events. The data aims to cover a wide range of possible instance spaces, with plans for future extensions to include more schools from across Europe. Here is a combined summary of pages 15 and 16 of the research paper. The authors introduce an extension to the XHSTT format to accommodate constraints present in modular high schools, providing 18 new real-world instances from German high schools and an ILP model to find feasible schedules. The ILP model is evaluated, and results show that using it as an exact method is ineffective, struggling to provide satisfactory solutions even with a 6-hour time limit. Only 10 out of 18 instances yielded solutions, which did not meet the criteria for a viable school timetable. The experiment highlights the complexity of the problem, suggesting that exact methods may struggle to provide solutions. The integral solutions obtained did not meet the necessary criteria, and Garobi's optimization capabilities were unable to provide lower bounds within the designated timeframe, preventing the assessment of the optimality gap. Despite these challenges, the authors believe that the ILP model's strength will be revealed when used as part of a heuristic approach, such as large neighborhood search, LNS. Future work involves exploring different exact methods, like SAT solvers, to determine if the problem is as hard as it seems or if ILP is not the right approach. The authors also plan to investigate possible new cuts for the ILP model and evaluate how heuristics developed for the original high school timetabling problem perform on this extension. Table 3 displays the outcomes of executing the 18 instances using the commercial ILP solver Gurobi, with a memory limit of 64 GB and a time limit of 6 hours. The objective value is split into two components of the form: hard, soft, constraint deviations. The results underscore the intricacies of the problem and the limitations of current methodologies. Here is a combined summary of pages 17 and 18 of the research paper. The authors propose an adaptive learning-based neighborhood search, LNS, approach to improve high school timetabling, incorporating methods from reinforcement learning. This extension aims to find better schedules by adapting to individual schools' needs. The approach will be supported by providing more benchmark instances from across Europe, along with a publicly available tool for validation. The authors will also compare future findings with actual school timetables to bridge the gap between theory and practice. The paper references various studies on timetabling problems, including integer programming techniques for educational timetabling, hybrid local search-based solvers, and modeling and solving university course timetabling problems. These references highlight the complexity of timetabling problems and the need for innovative solutions. The appendix provides a complete integer linear programming (ILP) formulation for the high school timetabling problem. The ILP formulation consists of several constraints, including general constraints, linked variables, and subevent constraints. These constraints ensure that the model accurately represents the timetabling problem and provides exact objective values. Specifically, the constraints include linking variables for student course day and student course day instance, ensuring that each student is assigned to only one course per day. Another set of constraints links variables for student course day and student course square sum, ensuring that each student has only one deviation indicator per point of application. The model also includes constraints for subevents, ensuring that each subevent is assigned exactly one starting time and the number of assigned resources equals the number of event resources. The ILP formulation provides a comprehensive framework for solving high school timetabling problems, incorporating individual school needs and constraints. By adapting this approach to incorporate reinforcement learning, the authors aim to improve the efficiency and effectiveness of high school timetabling. The research paper discusses the optimization of high school timetables, focusing on introducing individuality into student schedules. It presents a series of constraints and equations that aim to allocate resources and time efficiently for various events. These constraints are categorized as link variables, assign resource, assign time, split events, and distribute split events. The first set of constraints introduces new variables VT, R and WSE, R, which link the original variables with the new ones. These constraints ensure that each subevent is assigned a start time and resource, while also considering the total duration of the event. The second set of constraints, the assign resource and assign time constraints, apply to events. They ensure that each event is assigned a resource and a time slot, adhering to the event's duration and resource requirements. The third set of constraints, the split events constraints, are used to control the number of subevents and their durations within an event. These constraints utilize parameters bamount_c and bamount_k denote the minimum and maximum amount of events, and bdirk and bdirk_to represent the minimum and maximum duration of a subevent. Finally, the distribute split events constraints aim to distribute the subevents evenly across the available time slots. This is achieved by using parameters bc and bc to denote the minimum and maximum number of subevents, and dc to represent the duration for which the constraint applies. Throughout the paper, mathematical equations and algorithms are employed to model these constraints and optimize the scheduling process. The use of precise language and domain-specific terminology demonstrates the author's expertise in the field. However, the complexity of the equations and constraints may require a deep understanding of the subject matter to fully comprehend. The paper also includes figures, tables, and graphs that illustrate the concepts and results, providing visual aids for the reader. The overall structure of the paper follows a logical flow, starting with the introduction of new variables and constraints, then moving on to the different types of constraints, and finally discussing the optimization process. In conclusion, this research paper presents a comprehensive approach to optimizing high school timetables, incorporating individuality into student schedules. The authors employ advanced mathematical modeling and algorithms to ensure efficient resource allocation and time scheduling, making it a valuable contribution to the field of educational scheduling. The research introduces novel constraints for scheduling events, focusing on individuality in students' high school timetables. It begins by discussing the prefer resources constraint, which applies to events considering resource availability. The preferred times constraint ensures that events are scheduled within their preferred time slots. The avoid split assignments constraint and spread events constraint aim to optimize event grouping and distribution. The link events constraint connects events within groups, while the order events constraint regulates the sequence of events. Finally, constraints for avoiding clashes and unavailable times are presented. These constraints are formulated using mathematical equations and variables, showcasing a sophisticated approach to optimizing event scheduling. The research provides a comprehensive framework for creating efficient and individualized timetables. This section of the research paper discusses various constraints applied to resources and event groups in a high school timetabling model. It begins by introducing the limit idle times constraint, which aims to minimize idle times between events for each resource. This is achieved through the use of binary variables indicating whether events occur before or after a given time within a time group, and integer variables representing the total amount of idle times in a time group. The constraint ensures that the number of idle times does not exceed a specified limit. The paper then moves on to the cluster busy times constraint, which aims to limit the number of busy times within a cluster. This constraint uses parameters BC and BC to denote the minimum and maximum values specified in a given constraint, and it ensures that the number of busy times in a cluster does not exceed a certain threshold. Next, the limit workload constraint is discussed, which focuses on limiting the workload of a solution resource. The workload is calculated based on the duration and length of events, and the constraint ensures that the total workload does not exceed a specified limit. The balance class size constraint is also introduced, which aims to balance the size of classes within an event group. This constraint uses variables to denote the number of resources allocated to a specific event group and ensures that the difference in class sizes between two event groups does not exceed a specified parameter BC. Finally, the student choice constraint is mentioned, which applies to resources and aims to ensure that student preferences are considered in the timetabling process. Although not fully detailed in these pages, this constraint likely involves variables and parameters that capture student choices and preferences for certain events or time slots. Throughout these constraints, the paper utilizes mathematical equations and algorithms to model the relationships between resources, events, and time groups. The use of binary and integer variables, along with various parameters, helps to define and enforce the constraints that are essential for creating an optimal high school timetable. Here is the combined summary. The authors introduce a novel approach to individualize high school timetables by incorporating student preferences into the scheduling process. The model uses parameters BC and BC to denote the minimum and maximum values specified in constraint C element of C. The objective function, formulated as an integer linear program, ILP, aims to minimize the total deviation from student preferences. The authors introduce constraints to ensure that the produced schedule is valid and optimal, as shown in equation 111. However, the authors acknowledge that the ILP solver may provide suboptimal objective values if run with a time limit, due to the formulation using the is less than or equal to operator in combination with deviation variables. To mitigate this issue, they propose adding binary indicators to specify which constraint to use based on the current assignments. These indicators, binmax and binmin, are used to add constraints, 112 and 113, which enable the ILP solver to accurately calculate the objective value. The authors further extend this approach to handle constraints of the form x1 is less than or equal to s, x2 is less than or equal to s, xn is less than or equal to s, where xi may represent an arbitrary linear expression. They propose modeling these constraints using the max constraint, 114, which the ILP solver can automatically transform into a set of linear constraints. The use of general constraints, such as indicator constraints and max constraints, allows for a more flexible and accurate modeling of the timetabling problem. By incorporating these constraints, the authors can ensure that the produced schedule is not only valid but also optimal, taking into account the individual preferences of students. The proposed approach has the potential to significantly improve the efficiency and effectiveness of high school timetabling, providing a more personalized and satisfying experience for students.